Physics concepts like acceleration and deceleration are often best understood through real-world simulations. To illustrate these principles, we introduce two robots, Ruthie and Erwin, placed in a controlled environment where they must reach the door of an elevator. Their movements, dictated by acceleration and deceleration, provide an insightful look at velocity changes over time and how starting positions influence their travel. Furthermore, the nature of their movement, whether lazy or aggressive, demonstrates the impact of speed on reaching a target. Through this simulation, students can better grasp the effects of motion and how these concepts play a crucial role in everyday life. Ruthie and Erwin start their journey from different positions in a hallway leading to an elevator. Their task is to reach the elevator doors before they close. However, they are programmed with different movement behaviors, allowing for a diverse analysis of acceleration and deceleration. Ruthie is positioned farther from the elevator, requiring her to accelerate rapidly to reach her goal. In contrast, Erwin starts closer to the door, but must manage his speed by decelerating to avoid colliding with the closing elevator. Their movements over time create a vivid representation of velocity changes, with acceleration and deceleration affecting their progress. Additionally, both robots have settings that define how they respond to the need for speed. When set to lazy, they move slowly, requiring more time to either speed up or slow down. In contrast, when set to aggressive, they react instantly, showcasing a sharp contrast between gradual and rapid movement changes. When Ruthie is in her aggressive setting, she launches forward quickly, gaining speed almost immediately. Her velocity steadily increases, allowing her to cover more distance in less time. However, if Ruthie were set to lazy, she would take longer to gain speed, making her approach to the elevator slower and less efficient. This behavior demonstrates how different acceleration rates impact an object's ability to reach a goal within a given time frame. Erwin, on the other hand, faces the challenge of deceleration. Starting close to the elevator means he needs to slow down to avoid overshooting the target. When in the aggressive mode, Erwin decelerates rapidly, coming to a near-instant stop just before the elevator doors close. However, if set to lazy, his deceleration is more gradual, increasing the risk of missing the target altogether or having to adjust his movement to avoid an impact. This simulation highlights how acceleration helps objects gain momentum, while deceleration ensures they do not overshoot their target. The velocity of each robot changes over time, depending on the force applied to their movement. This variation in motion reflects real-world scenarios, such as a car needing to speed up on a highway or a cyclist slowing down before reaching a stoplight. Tracking the position and velocity of Ruthie and Erwin over time gives a clear picture of how movement changes. Ruthie starts at a disadvantage due to her distance from the elevator, meaning her acceleration needs to be significant enough to ensure she reaches the doors in time. If she does not accelerate efficiently, she will not make it before the elevator closes. Meanwhile, Erwin starts closer to the target, but must manage his deceleration properly. If he slows down too quickly, he might stop too soon and require additional movement to reach the door. Conversely, if he does not decelerate soon enough, he risks hitting the elevator at full speed. A velocity versus time analysis would show Ruthie's velocity increasing as she accelerates and Erwin's velocity decreasing as he decelerates. The difference in how their speeds change over time offers insight into the importance of timing and force application in movement. One of the most valuable aspects of this simulation is its ability to demonstrate physics in action. Students often struggle with abstract concepts like acceleration and deceleration when only presented through equations. By observing Ruthie and Erwin, learners can visualize how movement changes under different conditions. This kind of simulation has practical applications beyond the classroom. For instance, understanding acceleration and deceleration is crucial in driving, engineering, and even athletics. A runner who wishes to reach maximum speed quickly must accelerate efficiently, while a driver approaching a red light must know when to begin decelerating to stop smoothly. Additionally, such simulations help students develop problem-solving skills. By adjusting variables like starting position, velocity, and the level of aggression in movement, learners can predict and analyze different outcomes. This hands-on approach makes physics more engaging and relatable. The simulation of acceleration and deceleration using Ruthie and Erwin provides an interactive way to understand motion. Ruthie's need to accelerate quickly and Erwin's requirement to decelerate effectively illustrate the balance between speed and control. Whether set to lazy or aggressive, Their behaviors showcase the importance of timing and force in movement. Through this simulation, students can grasp how acceleration and deceleration impact everyday activities, from driving to sports. By observing velocity changes and the effects of different movement settings, learners can develop a stronger understanding of physics in a practical and enjoyable manner.